Hi, everyone. It is our pleasure to have Archana Venkataraman today with us. She's an assistant professor at the Department of Electrical and Computer Engineering at Johns Hopkins University. She directs the Neural Systems Analysis Laboratory and is a core faculty member of the Malone Center for Engineering and Healthcare. Dr. Venkataraman's research lies at the intersection of AI, network modeling, and clinical neuroscience. And her work has yielded a number of novel insights into neurological disorders such as autism and epilepsy, among others. Archana completed her bachelor's, master's, and Ph.D. in electrical engineering at MIT. She is a recipient of a very large number of fellowships and grants and a number of awards. In particular, she was named by MIT Technology Review as one of 35 Innovators Under 35 in 2019. I'm extremely glad to have you with us, Archana, today. And
Thank you, Neera, for that very kind introduction. So as was mentioned, I direct the Neural Systems Analysis Laboratory at Johns Hopkins. And very broadly, my group, we focus on developing new methods to parse neuroimaging and other types of data to understand neuropsychiatric disorders. And this particular talk is going to look at an intersection with deep learning, particularly in the regimes that we're working on where we have small sample sizes. So just to take a large step back and look at sort of deep learning. So deep learning has become ubiquitous across many domains from speech to genomics to imaging, vision, and it's fueled and propelled many innovations. And if we think about the rise of deep learning, there's kind of these two complementary pieces that have enabled that. So on one side, we have improvements in hardware and processing capabilities, as well as sort of connectivity in general, being able to distribute jobs and use cloud computing. But equally important, the rise of deep learning was fueled by data. So there was a critical mass of these large aggregated data sets, which really allowed these models and algorithms to learn. And in fact, if we just look at a very simple data matrix, and here this is very cartoonish just to illustrate a sort of a conceptual point where I've drawn complexity of the problem on the y-axis, and this is just a very sort of hand-wavy notion of complexity, and then the data set size or curation, so either sample size or the amount of supervision in terms of information humans have to interject. What we see is most of the problems that have gotten a lot of recognition and notoriety really fall in that lower triangle. So either they're very small data sets and they're just targeting a very simple question, or they can be targeting more complex questions, but we either need more samples or we need very careful human supervision in order for these algorithms to really sort of tease apart the different distributions they're looking at. Now, the issue is that there are many important problems that live in that top triangle, and I would argue that one of them is understanding the human brain, just as it relates both to normal functioning as well as atypical functioning. And so here is an outline for the presentation. So essentially, I'm going to talk about 3 different projects that we've been working on that span a range of applications as well as sort of translational utility. And I'm going to start with something a little bit more foundational. So this is one of my bread and butter projects, a lot of work that's been driven from my PhD and postdoc. And this is looking at connectomics and how it relates to particularly autism, but also other developmental disorders. So just for those of you who are less familiar with functional connectomics, the data modality we're interested in is called resting state functional MRI, or resting state fMRI. And we can think of fMRI as essentially a 4D acquisition, where on one hand, it's a collection of volumes that are sampled over time as different physiological signals may be changing. And on the other hand, each spatial location or voxel has an associated time course. Now, for resting state fMRI, this is a passive acquisition. So the subject is just lying passively in the scanner and the data is being acquired. And really the feature or the metric of interest that most people focus on is a correlation or some notion of similarity. So I've just drawn I've written the simple correlation coefficient on the slide. And it turns out by looking at these correlations, we can actually start to tease apart the organization of the brain into different functional systems. So on the slide, we have motor, default, and visual system, and these were just identified by a seed-based correlation analysis. Now we can take this, and then from these correlations or these correlation measures, we can conduct some sort of neuroscientific or clinical inference, either using statistical methods, so just doing group comparisons, or different clustering techniques to try and subdivide the brain into regions or into networks. Now, essentially, machine learning has become actually quite popular for resting state fMRI. And so this moves beyond sort of group-wise statistical analysis or clustering methods and really looking at patient-level prediction. And so most resting state fMRI pipelines have two steps. First, there's taking the resting state fMRI features, typically a correlation matrix, and reducing and doing some sort of dimensionality reduction to extract some salient features or salient patterns from the data. And then second is a predictive model in which we can, which is used to take those reduced feature spaces and learn a clinical measure, most commonly case control diagnosis. Now, there are several techniques that have been used for both of these components. So very simple dimensionality reductions include principal components or kernel principal components. A little bit more complex ones use independent component analysis or dictionary learning. And then on the prediction front, there's linear regression models, random forest classifications. And then, of course, in these days, many folks are looking at end-to-end pipelines that kind of simultaneously do those. Using deep neural networks. Now, one issue with just in general, this combined approach is we typically get either good group level information, so we're able to capture these subnetworks, or sort of we can focus on the patient level prediction in which we might get a black box algorithm that does both, but doesn't really predict but doesn't sort of explain or interpret the data itself. Now, an added layer of complexity in terms of these fMRI analyses is that the brain is not static. So over the course of the scan, there's increasing evidence that the brain is transitioning between different states. And in each state, there are different subsets of networks that are sort of simultaneously active or suppressed. And so there are many models that have been used to try and tease apart these dynamics. So starting with hidden Markov modeling to just capture state transitions, dynamic conditional correlations, which are sort of dynamic connectivity measures, and just variations of graphical lasso, et cetera. Now, another aspect is that many works just focus on the functional connectivity in isolation, but it turns out, of course, that sort of the brain is not just generating these functional signatures. There's actually an underlying anatomy and structural regularization. And so one way we can sort of probe or assess this is using diffusion MRI. So this is a different acquisition that essentially tracks or measures the diffusion of water molecules through the brain. Then sort of the underlying assumption is that water diffuses more freely along fibers rather than across them. So from diffusion MRI, we can run a sort of a tractography algorithm, and similar to function where we have a connectivity or correlation matrix, we can create a structural graph. And then many works actually use this diffusion pipeline to do some subsequent clinical inference similar to function. Now, existing machine learning approaches that try to do structure and function integration are a bit pipelined in the sense that they run feature extraction separately on the two modalities and then sort of train a discriminative or predictive model on those features and draw correspondences between the data sets post hoc. And sort of this ignores effectively the difference in what sort of information the data is telling you, as well as sort of underlying assumptions about how they might be related. So with that as a backdrop, what I'm going to introduce is a model that actually combines deep learning and generative modeling in sort of a hybrid optimization scheme. And so it starts with this is the model overview. And effectively, the top component is how we represent the connectivity data. And then the bottom component shows our predictive model. And this was published in MICAI in 2020. I should also note that this work was done by my graduate student Niharika at Johns Hopkins and our collaborator Stuart Mostovsky at Kennedy Krieger. So I'm going to start with the top block just to describe our data representation. So if we think about our input connectivity data, essentially we have these correlation matrices, which I've denoted gamma TN, so for patient N or subject N. What we're going to assume is that these dynamic matrices can be represented by a set of subnetworks, sort of a combination of subnetworks, which are fixed across the cohort and for all time. And then, so for just in terms of representation in this matrix B, each column essentially can be projected onto the brain as a heat map, and it tells you which regions are sort of coactive versus sort of antisynchronous. Now, these subnetworks are combined to generate these connectivity matrices via these temporal loading weights, which are Cn. And so this is just a mathematical representation, but you can think of them as diagonal matrices that vary over time. And we're going to call them patient network strengths. So these are patient specific. And then just to get the data representation, this is an outer product decomposition because the input matrices are symmetric. So effectively it's B, C, B transpose as our representation. Now, we'd like to incorporate some structural regularization just to sort of emphasize that the underlying structural connectivity or structural pathways in the brain actually have some relevance in how the function should be represented. And so what we use is a structural regularizer that's effectively based on the graph Laplacian computed from the DTI data. And I'll just describe how that sort of in a later slide, how that actually enters into the optimization. But essentially what it tries to do is it tries to emphasize in our loss function the connections for which there is underlying anatomy and then downweight the other connections. So I've described the top component, which we've called a structurally regularized dynamic dictionary learning. So that's the representative term. Now, the bases themselves are fixed for the population, so that gives us sort of interpretability or sort of biomarkers in the brain. However, the temporal loading coefficients or the weighting coefficients are subject specific, and effectively we're going to try and use those to predict cognitive deficits. So in the prediction block, we're going to start by effectively stacking the patient temporal coefficients, so time just for representation. The bases are on the vertical dimension and then horizontally is time. And so every vector is the diagonal of the matrix from the previous slide. And we're going to feed those as inputs into an LSTM. And here the hidden representations are going to be fed into two separate networks. There's a predictor network, which is trying to output the clinical measure of interest. And here we just use a very simple, very small, fully connected ANN architecture. And then there's an attention network, which is very similar to the predictor ANN, but we use a softmax so that effectively it's going to select out different time components. And here we use just a weighted combination of these predictions to output the clinical measure of interest. And I will note in this particular work, we're trying to simultaneously predict different behavioral deficits. And so from a clinical standpoint, our motivation is trying to obtain a broader characterization of a disorder like autism, which has many different deficits along different dimensions. So here's our final model, just as a flow diagram. And if we look under the hood a little bit, our objective function, J, has several terms. So here we have the structurally regularized dynamic dictionary learning loss. So this is how well that representation, the outer product representation captures the original data. And I'll just note that this is a weighted Frobenius norm by the graph Laplacian. And effectively what this does is, if it was a typical Frobenius norm, it would essentially be an isotropic loss, where the loss on every dimension was weighted similarly because we just have a combination. But with that structural reweighting, effectively what it does is there's this inner Laplacian multiplication, which kind of compresses this loss function. So it emphasizes directions roughly along which there are anatomical connections, and it sort of de-emphasizes other directions for which there is no anatomical connection. Now, the second component of the loss is our prediction term. And so this is how well the deep neural network can predict the different scores based on those patient network strengths. And we also have a constraint that the patient coefficients must be greater than or equal to 0, and the bases are orthogonal. So the inequality constraint is just given by the fact that our input data is positive semi-definite, and then the the orthogonality gives us greater representation power for the same number of bases. So they must capture sort of orthogonal information. Now, just in terms of inference, so this is a joint optimization. So the inputs are going to be the correlation matrices, the DTI graph Laplacians, and the behavioral scores during training. And then from that, we're going to solve for the bases, the temporal coefficients, the neural network weights, and the neural network weights. And so essentially we use an alternating minimization approach where we update B using a the update for B has a closed form using a Procrustes solution. And then we effectively use a stochastic atom update for C, and then update theta, or the neural network weights, using a standard atom optimizer. And I'll note that this coefficient C is actually what ties together the deep learning component, which is the LSTM, and the generative component, which is the dictionary learning. So in that update for C, we actually get a fusion of those two data terms, or those two loss terms, which are sort of a fusion of the information in those two representations. And just based on how that gradient evolves, we can actually just use atom as an easy way to optimize. Now, in terms of our data set, so we're just evaluate this model on neuroimaging data of resting state fMRI and diffusion MRI for 58 ASD patients. And what we're going to try and predict in the behavioral domain are a combination of three, well, essentially separately together, three different scores: ADOS, SRS, and Praxis. So one thing to note is that the administration modalities for these scores are very different. So ADOS is a behavioral exam by a trained psychologist who evaluates the child. SRS is actually a parent report. So the parents or the caregivers are given a questionnaire and they need to fill it out based on their observations. And then Praxis, it just evaluates effectively visuomotor integration, so hand-eye coordination, gesture imitation, which are known to be tricky for children with autism. And then finally, we use five-fold cross-validation to try and sort of evaluate predictive performance. Just for a sort of a baseline comparison, we compare with two different approaches. The first is the multimodal BrainNet CNN. So the BrainNet CNN was designed for, it's essentially a neural network where the convolutional filters are, instead of grid-based filters, are just cross-shaped. And this is designed for essentially connectivity matrices. And then the other is data-driven feature extraction, where we essentially combine the two data sets and we use PCA to get a feature representation, and then use the same LSTM to do deep multi-score prediction. So I'll just show you the results of BrainNet CNN first. And so here on the bottom, I have three scatter plots. The left one is for ADOS, the middle is for SRS, and the right is for Praxis. The red points are training and the blue points are testing. And so what we note here is that in general, the training performance is pretty good for at least two of the measures. However, the testing performance, when we actually move to unseen data, just collapses, and effectively it's uninformative. And a very similar behavior happens with the PECA and LSTM-ANN. So again, in general, training is pretty good for all 3 scores combined, but testing collapses for 2 of them. And I'll note that this behavior is fairly consistent with most baselines. So this idea of predicting different scores or different clinical attributes simultaneously is actually quite challenging. And so in general, we can tune parameters of these 2 baselines to predict one of the scores reasonably well, but then it will fail on the other 2 scores, just based on the difficulty of the problem. And then finally, we have the results of our method, where again, training is very good, but here we're actually able to capture something informative in terms of testing. Both the median absolute error is lower and normalized mutual information tends to be higher. So beyond the quantitative metrics, one thing that's really nice is that our model also gives us these bases B, which can be projected as subnetworks onto the brain. And so here I've just illustrated 4 of the subnetworks that were obtained by our joint model. And as you can see, these 4 subnetworks map onto fairly well-known systems. So our model is able to really extract information that is reasonable in terms of being associated with the current autism literature. And then finally, we just can study the dynamic evolution by looking at the sort of the attention weights of the ANN to see which time intervals it focused on, and then the patient network strengths. And so on the left, we have the attention weights for the ANN. And what we notice is that across patients, which are stacked vertically, the model is actually picking up different time intervals as being relevant for its prediction, which suggests that really the brain is, well, it supports our hypothesis that the brain is really transitioning between states, and there are only a few states of interest that are really useful for the prediction or for the manifestation of the disorder. And then on the right, for a single patient, we've just illustrated the network strength C, just to show that these strengths do vary and they do phase in and out across the scan duration itself. So the first project was really kind of in the realm of connectomics, and it really focused on biomarker discovery and trying to capture and understand just at a high level or an exploratory level, deficits associated with neuropsychiatric disorders. The second project is a little bit more translational, but here again, we have this issue that we have limited data, and our solution again is to blend deep learning and generative modeling. So this particular project focuses on epilepsy. So epilepsy is one of the most common neurological conditions, and it's associated with a 5-fold increase in mortality. Now, while most cases of epilepsy are treated with medication, between 20 to 40% of epilepsy patients are considered medically refractory, meaning they don't respond to different combinations of drugs and they continue to have seizures. And really, for these patients, really effectively subsequent therapy depends on us being able to detect and localize the seizure activity in their brains. And here, EEG or scalp EEG is probably the first and foremost tool used by clinicians to try and sort of subtype, characterize, and understand and plan out therapeutics for these patients. And what's interesting is that despite sort of decades of signal processing and machine learning research, this procedure of analyzing the EEG is almost entirely done by manual inspection. And so what I mean by manual inspection is, well, effectively this. So a trained epileptologist, well, essentially the epilepsy patients will go into the hospital and they'll have scalp EEG, sort of electrodes attached to their brain, and they'll be monitored in the hospital for several days while they're having seizures. And so after the fact, what an epileptologist will do is effectively they'll visually scan. So they'll stare at hours and hours and hours of these EEG recordings to try and manually identify where and when the seizure is coming from. And so the reason that this manual procedure is still the gold standard is actually, it becomes obvious very quickly. And so the reason is just if I were to show you this slide, as effectively non-experts in this domain, if I were to say that there's a seizure occurring some point on this slide, the most common answers would be either the high amplitude strip in the middle or these really atypical signatures on the right. And unfortunately, both of those are incorrect. So both of those are actually artifacts. And in fact, the seizure signal itself can be very subtle. So in this case, it's kind of a rhythmic oscillation that's occurring in that upper channel. And so if we think about a deep learning model or a machine learning model, it's very easy for them to grasp salient differences and really salient and prominent features in the data. And in this particular application, they're probably going to be wrong, right? And so this is why it's a very challenging problem for automated methods. Now, with that said, there has been quite a bit of work on automated seizure detection. And in general, these methods follow a very simple pipeline. So we have raw EEG data that's pre-processed, and then there's a feature selection component and a classification component. And by and large, over the last 2 decades, the majority of work has focused on feature selection. So trying to develop and hypothesize features that extract relevant information to the seizure. So common features include time frequency information that's obtained by short time Fourier transforms or wavelet analysis, as well as nonlinear features that try and extract effectively entropy in the signal, because that is believed to be associated with the onset of a seizure. Now, despite all of this work and the fact that there are some commercial seizure detectors, they really haven't replaced manual inspection. And one of the main reasons is that just the incredible patient variability and heterogeneity across this cohort. So our approach is to take a slightly different tack here. So instead of just trying to make a detection at every point in time and saying the seizure is starting, our approach is actually to think, okay, this seizure is not beginning in isolation at a point in time. It's actually sort of an evolution of atypical information that starts somewhere in the brain and then propagates. So can we hypothesize a model of this spatiotemporal propagation and effectively use that model to backtrack or reverse infer the onset? So in this, we are going to take a Bayesian modeling approach in this particular project. And this is work that was done by my graduate student, Jeff, at Johns Hopkins, and our collaborator, Emily Johnson, in the Epilepsy Center at Johns Hopkins. So effectively, these Bayesian models, we can think just in broad terms of them having 2 components. So on the top here, there's a latent template. And so these templates specify unobserved phenomenon in the model or in the particular application. And in this case, we're going to say this latent template will capture the spatial propagation of seizure activity. And then as a complement to that latent template, there is observed data. And in our case, that data is going to be features of the EEG signal. So this is noisy measurements that we can use to effectively infer that latent template. And then, of course, these 2 layers are all tied together via probabilistic interactions, which gives us essentially the tools of inference to be able to make a decision. So just going into that latent structure, the seizure propagation model. So we're going to start with sort of our model of how a seizure evolves. And it begins with this 1020 system. So this is the most common electrode placement system used in clinical settings in the hospital. And it just consists of the channels placed in such a fashion here. And on top of this system, we've traced in these blue lines. And that's really going to specify a graph that underlies these nodes. And specifically, we've connected neighboring electrodes and interhemispheric electrodes. So the neighboring electrodes just capture the fact that in general, seizures tend to propagate locally. And then the interhemispheric ones allow for just jumps across the hemisphere, which is actually a common confound in manual inspection of EEG. Now, as for the model, we're going to assume that everything starts in baseline. So in terms of the data, we're assuming it's starting at a point where there's no seizure. And so all of the channels are green in this case. Now, as time evolves and time marches on, at some point, a channel is going to become atypical. So we're going to say it flips into a seizure state, and this is shown by the red T5 electrode in the bottom. And then over time, as time goes on, this seizure activity is going to essentially evolve or propagate through the graph to other channels. And we don't make any assumptions about how far it will spread or where it will start, but we just want to capture this type of behavior. Now, if we kind of trace this to sort of a mathematical construct, this is linked to temporal modeling, and one of the most classic temporal models is the HMM. So in a hidden Markov model, we effectively have a latent state and an observed data, X and Y. And this process is specified by two distributions. So first, there's an emission likelihood, which is how the data Y is generated from the hidden state. And then there's a transition prior, which is how the hidden states evolve from one time step to another. And so just based on these two distributions, we can march that chain on as long as we want in time. And then what's really nice about this HMM is because there's effectively this kind of one-stage process between nodes, we can very easily, from the data, infer that hidden state information using the forward-backward algorithm. So effectively, we're going to pass messages or information one way in the chain and then pass it backwards. And by sort of iterating this process, we can obtain likely state sequences or likely individual states. Now, if we map it back onto our problem, every channel is going to be a hidden Markov model. So every electrode here is its own HMM. And since we have a lot of electrodes in this EEG montage, we have many HMMs. Now, an added layer of complexity is that in addition to just these many HMMs, we have connections between them through that blue graph structure. And so this is going to very tightly couple all of these chains along that hidden layer. So if we look at the overall joint data distribution, we effectively have two terms. So we have one term that is how the observed EEG signal is generated from the hidden state. And then the second is a propagation dynamics, which is a little bit more complicated than just a traditional HMM. And I'm actually going to start by formulating that portion first. So effectively, in our model, we're going to assume each channel can take one of three states, either pre-seizure, seizure, or post-seizure baseline. And so just a very simple three-state HMM. And what we want is that we essentially want, at the next time step, channels to be influenced by their neighbors on the graph. And so if we, on the bottom, there's the little grayed out channel T5. If we focus on that channel, in this particular case, all of its neighbors are green, so they're all in a baseline state. And so there's a small probability that it's going to transition to seizure. Now, if some of its neighbors were now in a seizure state, well, that sort of increases the probability that it's going to transition into a seizure state. So if we think of the sigmoid, it's just going to be a higher probability on that curve. And then finally, if all of its neighbors are in a seizure state, then again, in the next time step, the model really wants to encourage that particular electrode to transition as well. And so we have a higher transition probability. Now, if we just go back, and I've put the data term on hold for a second, inference is actually very difficult, regardless of whatever that likelihood term or that data term is. And so our strategy is to approximate our joint distribution or approximate the posterior that we're trying to solve for, which is Px given Y, with an easier distribution. And effectively, we're going to use just a variational mean field approach. Basically, we assume our posterior just breaks those links between the chains. So it's just our posterior is effectively a sort of individual HMM chains. But these functions C are actually going to depend on the neighbors during inference. So if we just kind of plug this framework as a latent structure into our Bayesian model, now the term that I just have omitted was how do we get the data? And so we've looked at many iterations of this. So in the earliest work, we just assumed very simple spectral features as the EEG data. And we modeled the likelihood as a mixture model, so just a parameterized likelihood distribution. But EEG itself is very complex, as I showed on one of the earlier slides. And so it turns out instead of doing this kind of parametric feature selection and parametric model, we can replace the entire process with a neural network. And so this is work presented at IPME a few years ago. And here, effectively, we're going to use a convolutional neural network as the likelihood to the graphical model. So there's one subtlety in terms of using a neural network for a likelihood, and that is as follows. So a neural network, a CNN by design, is actually a posterior inference engine. So if you think about how it works, effectively you feed in the data Y, some snippet of EEG, it gets passed through these convolutional layers, and the output is usually a class probability, which you can then threshold to get a sort of a discrete class. And the issue is that what we really want is the likelihood. We want the opposite, essentially the opposite conditioning. And so we can obtain this factor by rescaling using Bayes' rule. So essentially we take this likelihood, and by Bayes' rule, it's equal to the ratio of, on the numerator, we have the CNN output times the probability of just observing the data. And in the denominator, we have the seizure prior. Now, this PEEG term, so the PY term, it's going to be constant regardless of what the seizure class is. And so when we are actually going through these inference solutions, most of those updates are ratios. And so that factor is actually going to cancel out. And then that means our likelihood is just proportional to the CN output divided by the seizure prior. And for inference, that's all we need. Now we can approximate the seizure prior just empirically. So in our training data set, we can take just the ratio of the number of time windows with seizure versus the number of total time windows and obtain this factor. And so then we can use this rescaling trick essentially to plug in the neural network as our likelihood. So the data here that we used for evaluation is two data sets. One is clinical EEG data collected at Johns Hopkins University. So these are 15 patients with focal epilepsy. And since they were monitored for several days in the hospital, they actually have multiple seizures. And so we have 90 seizure recordings total across these 15 patients. And the other is a publicly released data set from the Boston Children's Hospital. Here, it's unspecified seizure types, so they could be focal or they could be general. And we have 24 patients and 185 seizure recordings. We're just for baseline comparison, we're going to actually look at two versions. The first is this coupled hidden Markov model with the Gaussian mixture model likelihood. So that's the same Bayesian prior, but then using the parametric likelihood that we had done in our previous work. And then the other is just using the neural network to effectively classify seizure versus baseline. So testing how much influence that smoothing prior or that propagation prior has on the analysis. So these tables just illustrate the detection accuracy of each method. So on top, we have the JHU data set, and on the bottom, we have the CHDI data set. The particular model that I just described with the hybrid generative and deep learning components is in the top row, the PGM-CNN. And you can see on the JHU data set, it pretty much outperforms the other baselines in terms of AUC, F1, and true positive rate. False positive is on par, and so is precision with the version without the neural network likelihood. And a similar trend you can see on the CHB data set as well. Now, if we just look at a qualitative map to try and understand where some of the failure points for each method are. So here I've illustrated a single seizure during testing for each of the three methods. And the EEG channels are stacked vertically while time proceeds on the horizontal axis. And so the red area is the sort of the predictions or seizure detections made by each method. And so what you can, and the black vertical lines are from the clinician, kind of where their rough boundaries of the seizure were. So I think a few things to note. So first, this the smoothing prior, so this latent, essentially latent propagation model, sort of fills in many of the gaps. So it provides contiguous detection, whereas for the CNN and the CHMM, there are breaks in terms of the detection. There's also the CNN. So if we think about just for every time window making a seizure versus baseline detection, we see a lot of uncertainty. So there are just a lot of red flecks throughout the entire image, which means that the deep network is essentially turning on, turning off, turning on, turning off in very rapid succession, just based on the characteristics of the data. And so that illustrates that this data set, this type of data is very noisy. And so a simple classifier is going to have difficulty discriminating between the two classes. And also the CHMM, we have a couple of misses in that it turns on after the seizure boundary, probably due to post-seizure artifact. Which highlights the fact that the neural network is able to capture more complicated signatures from the data, which might be missed if we just focus on these sort of pre-selected features and a parametric likelihood. Now, I had previously shown just detection results. One really exciting part of this model is that this propagation latent structure actually gives us a first look at how we might do onset zone localization. So trying to figure out where the seizure is coming from on the scalp. And in fact, if we actually, so what I've highlighted here are just for two different seizures, the inference is made by our joint hybrid model during testing time. And what we can note and what we were able to do post hoc is really understand and show that, well, first of all, these are very different. So the model is able to learn different seizure signatures and different seizure propagations from the data. And also they do correspond with clinical annotations, meaning the model is able to correctly identify where the seizure is coming from. And it's able to give us this kind of fine-grained propagation information, which we might not be able to get from visual inspection, all on data that it hasn't seen before. And in fact, our current work and our our next iteration, as well as our current work, is actually trying to do this simultaneous detection and localization. So in this particular work, which was presented in MICI in 2019, what we did is we essentially decouple the detection and localization problems so that for detection, the model could use more data to learn. And once that sort of model made a detection that a seizure was beginning, it would initiate this spreading model to try and tease apart the onset. And from here, we've been playing around with essentially more graph neural network based approaches, again, to try and sort of accommodate and model these propagation patterns in the data itself. Finally, this is just a plug. So if you are working on EEG, and especially problems like seizure detection or even other types of EEG data sets, we've developed an EEG visualizer that allows you to look at the time series and actually run PyTorch, a deep learning model on the data itself and plot the output visualizations. So this is freely available for download at my website. And of course, you're welcome to play around with it. So in the last 15 minutes or so, I want to highlight the third project, which is also kind of a deep learning generative modeling hybrid, but it doesn't focus on imaging. And in fact, here, this particular data set is on speech, and our goal is to automatically amplify emotional cues. So if we just take a step back and look at sort of a system theoretic abstraction of perception, we effectively have three blocks. There's a sensory input, there's a brain, and then there's how the signal is perceived. And in fact, part of the previous talk was actually kind of how do we parse the brain itself, which is we can use neuroimaging data and EEG to parse that, or to at least try and understand that. And for perception, we have behavioral assessments. So these could be either clinical evaluations or sort of queries. But one interesting thing to note is kind of what that begs the question, what about the sensory input block? And in fact, can we actually play around with that block to alter perception systematically? Right. And so by sort of designing algorithms that can do that, that might give us a conduit to actually study perception in a quantitative setting, behaviorally, as well as just fold it into future neuroimaging studies to see what's going on as we vary stimuli. So with that as a backdrop, our goal in this particular project is to automatically manipulate emotional cues in speech. And the underlying motivation here was just to develop a tool that can be used to study emotional processing deficits in autism and actually PTSD, and potentially to pave the way for new therapeutics. So before I do that, so in order to study this sort of emotional manipulation strategy, one can think that it requires certain type of data. And in fact, it might require data in which we have the same thing or same sentence or words being said in different emotions, so we can effectively extract and understand what's causing that differential. And it turns out that there are not many data sets available. And so we actually collected one in the lab. And so we call it the VISIS data set. So so effectively, we developed a script of 252 phrases. And then we hired actors from Baltimore to come into the lab and essentially read the script in different emotional classes. So neutral, angry, happy, and sad are the ones that we're going to talk about primarily in this work. And then once we had that data, just to understand perception, we actually crowdsourced that on Mechanical Turk to obtain human annotations across a larger sample size of what do they think the emotion of that particular utterance is. And from here, we can use that data as a starting point for these types of experiments. So now if we go into the modeling itself, and we look at speech. So this is just a speech utterance that I've plotted. It kind of reminds us of noise with an envelope, right? So there's all sorts of really, really high frequency oscillations, but then there's an overall shape. And it turns out that's not a bad way of thinking about speech in general. And in fact, it's actually used the primary way that folks analyze these types of signals. And so we can use a standard vocoder, in this case, the world vocoder, to decompose the utterance into three different things. So first is the spectral envelope. So this is time frequency information. The second is aperiodicity, which is roughly the deviation from effectively rhythmic or from a purely rhythmic signal. So that's the noise component. And then finally, there's the pitch contour. So this is how is the main mode or the fundamental frequency changing over time. So the spectral envelope, it turns out, is actually very important for speaker identification. So every person has their unique spectral signature. But for emotion, actually the pitch contour is what is the primary signal that conveys it. So the differences in intonation over time is by and large what conveys emotion. And so we'll focus on this pitch contour and effectively modifying this pitch contour. And so our strategy is actually to think of these pitch contours as perturbations of each other. And just borrowing from medical imaging, if I just show you a source and target pitch contour, so these are just the pitch contours of two utterances, the same utterance by the same speaker, but one in a neutral setting, which is the red, and then one in a more emotional setting, which is the blue. One thing we could try and do to modify emotion is align them. And then borrowing from sort of common techniques in medical imaging, one strategy to do so is to register the two signals. And so we can think of registering them using a 2D curve registration approach where we're going to shift the pitch contour in the horizontal axis, either up or down, and then we can actually vary that shift over time in order to get the signals to align. And so the overall framework that we use is LDDMM. So the nice thing about LDDMM is we can constrain it to 1D vector fields, and it's parameterized by these little momenta vectors. So we can think of those momenta as initial trajectory. So this is a low dimensional target that we can actually try and predict or learn using a deep neural network. And then once we've learned that, we have a deterministic warping function that is smooth, well-posed, etc. Now, the way we're going to tackle this in this particular work is actually using a cycle GAN. So we're going to sort of use a cycle GAN so that we can train this in an unsupervised or non-parallel fashion. And so in a cycle GAN, we can think of it as you take a generator, you take your target data, your source data distribution X, you train a generator to transform it into your target distribution Y, but then you also train a second generator to go back to X, right? And so in that fashion, the loss function is just how well the actual cycle works, just starting and going from X to Y back to X. And then there's a discriminator that takes that middle block and determines, is it real or fake? Now, this is a sort of a pointwise loss function. And what we're going to do is, instead of it being pointwise, I think here, we're actually, instead of individual points transforming from X to X hat and back, what we want is we want the overall data distribution. So that kind of the distribution of points in the source of motion X to kind of match that distribution of points in source of motion Y. And we do this by adding a KL divergence term between the original and then the reconstructed sort of distributions in both directions. So both from X to X prime, X hat, as well as from the target distribution going from Y to Y hat and back. And so just by using sort of Jensen's inequality and that KL divergence term, it turns out we can actually derive what we call a variational cycle GAN. And so here, what it does is we can use the same cycle GAN setup, but our discriminator, instead of taking a pair of utterances and determining is it real or fake, what we do is we take a pair of utterances and the discriminator tries to determine which distribution it belongs to. So if we think of, we have now a generator and a discriminator. So the input to the discriminator are going to be two utterances, A and B, and it's going to output a distributional loss. And we just model that as a standard convolutional neural network with some sort of instance norm and downsampling. Now that generator is actually going to be a sort of two components. There's going to be a deep stochastic block, which we use to learn these momenta functions for the LDDMM. And then there's LDDMM itself, which we can implement as a recurrent neural network with fixed weights. And those weights we can fix a priori just based on the kernel sizes and the kernel definitions in LDDMM. So what's really nice is that because it can be implemented as a recurrent neural network, we can actually backpropagate right through LDDM, and during training, actually update the parameters of that deep stochastic block as well as the generator. And so here is just quantitative results. So here our goal was to take neutral utterances and transform them to either angry, happy, or sad. And on the top, we have emotional saliency. So once we've transformed them, we did a crowdsourcing experiment to see how do raters view these particular signals. And then on the bottom, we have the mean opinion score, which is just how do they rate the quality. And so we've compared this against a very standard parametric Gaussian mixture model by LSTM, and then a cycle GAN without our variational term, and then our method itself. In general, we can see that from an emotional saliency standpoint, for angry and sad, our method does better than all of the baselines. And for happy, it's a little bit worse than the cycle GAN, but because of the way we had subsampled the data set, there are actually less utterances for happy, so it might be a sort of a data issue. And just in terms of the speech quality itself, our model is always as good or outperforms the baselines. And so let me see, I do have some sample audio, so we can see if it plays. So this is a neutral to angry conversion. Here's the neutral signal.
4th of July.
Was that audible to everyone? Yes. So this is the actor saying
4th of July.
4th of July. And then after we use this registration framework, we have
4th of July.
So what we notice is that there is an increase in pitch, which is very typical. So the pitch variation tends to be much steeper in angry signals. And so our model is able to learn that automatically. Here is neutral to happy.
9,
So there's an actor saying 9. Let's see.
9,
And then after conversion, let's see. Oops. Let's see.
9,
So there's essentially a lift in the pitch contour towards the end, which is one of the ways that folks convey happy.
9,
And then neutral to sad.
They smell
So
bread.
this is an actress saying they smell bread.
They smell bread.
And then in our conversion, our model is able to learn to put a tremor in the voice, which in terms of what it learns mimics some of the characteristics of sadness. So before concluding, I'd like to acknowledge my fantastic lab, our collaborators and our funding sources, and everyone underlined actually contributed to the development of this work, or what I presented in this talk. So just to conclude, I've presented 3 different projects in vastly different application domains and data domains. And the common theme is that we really have small, limited number of samples available to learn the patterns that we're interested in. And so in each case, we kind of leverage this hybrid structure between a generative or a classical generative model, as well as a sort of a deep learning component, in order to be able to parse complex information from the data while still not overfitting to it and providing some sort of interpretability at the output. So with that, I'm happy to take any questions.
Thanks a lot, Archana, for the fantastic talk. Are there any questions?
Can you hear me?
Yes.
Thank you very much for the great talk. It was, all 3 projects were really interesting. I wanted to ask for the first part, maybe I missed it, but did you mention why there's a big discrepancy between the test and training performance?
So just in general, first, we're in a very small data regime. Let me see if I can make it back to that slide quickly. So just in general, these are all over parameterized models. So it's able to, just based on limited sample size, overfit quite easily. One thing is, so just the way we've displayed the training results. So what we've done is just used, essentially, during training, there's a little bit of difference in the procedure of training and testing. So during training, we can feed in all of the information and go straight through. But during testing, what we actually have to do is we have to solve for these intermediate patient network strengths and then independently run the deep neural network to get the output prediction. So if we actually use that same testing procedure for the training data set, the distributions have a little bit more of an overlap, so it's not quite as overfit. But the short answer is all of these are over parameterized. And so that's also one of the reasons that the baselines cannot adequately basically predict all 3 scores simultaneously.
Thank you.
Yeah.
Can I also ask another question regarding this project?
Yes.
So basically, now you're learning a linear dictionary?
Yes, it's a linear dictionary, yes.
Would it be also possible to use networks to sort of learn a sparsifying or whatever transform instead of learning the dictionary in a linear fashion?
So we have not looked at, in this particular framework, we have not looked at a nonlinear dictionary. We've looked at nonlinear prediction models. And the reason is that even the linear dictionary, it's a little bit analogous to like an ICA map in that it gives you sort of a sub-network. And so we're just sort of using those sub-networks as sort of the biomarkers extracted by the model. And just based on, effectively, if you do a scree plot, I don't know how much you would get from a nonlinear basis. We have looked in other work subsequent to this, just using graph neural networks from end to end. I would say in terms of predictive performance, there's a slight boost, but really nothing particularly noticeable. So I think we are hitting the limit of what the data can tell you about the different measures of interest.
I see, especially probably considering that you have very low amount of data. Learning something with only end-to-end, it's not really possible.
Yes, I mean, I think there's issues of the sort of data set size, but I also think there's issues in terms of how informative the data distribution is ever going to be. Like, even if you had a large data set, there is a question of how much it can tell you about the score of interest. And so that I don't think I have a good answer to, but just based sort of on the literature, I don't think fMRI is going to give you perfect predictive performance. And so the question becomes, what is the other utility? And so for us, the simultaneous score explanation, as well as being able to extract interpretable biomarkers, is relevant.
I'm sorry, I asked too many questions, but just one more burning question, if I'm allowed to. It's also how reliable are the structural connection information which you extract from the diffusion MR, because if you use that also to sort of give the structure onto the functional connectivity information, and if it is incorrect, it might lead to big problems, right? Can you comment on that as well, please?
I agree that there's definitely well-known issues with tractography, and of course having severe estimation error of your tracks is going to impact your model. I will say, and potentially I skipped over this in the data slide, or I didn't include it. We're looking at an ROI-based analysis. So these are not voxel to voxel connectivity, but region to region. And those regions are relatively large. So we're hoping that if there is a little bit of noise at the voxel level, it'll sort of average out when you move to a large region for a larger parcellation.
I see. Thank you very much.
I have a technical question about this project.
Sure.
So you, in the slide where you showed the loss function, you mentioned that the C matrix is constrained to be non-negative, right?
Yes.
Yes, exactly. How is this ensured? Is it by clipping the values at 0?
No, it's actually at the output here. When it's implemented, we do the estimation and then feed it through a ReLU. Yes, effectively, we feed it through a ReLU during. So that's, I see. So the C matrix is also is outputted by a neural network, is it? So effectively, we're using alternating minimization. And so this is just a sort of, we take a gradient and we're updating it using Atom. So after it updates once, we can then effectively threshold it for the next step. Yes, I see. Yeah. So so the input to your neural network, can you go back, sorry, to the flowchart that you had in the previous slide? Sure. So the flowchart is the generative, this is the generative process. What we're actually trying to do is we have an objective function. During optimization, we're going to spit out a B matrix, right? A bunch of C's, and then the neural network will train. So the LSTM weights will train. So the neural network itself is just the LSTM.
Right.
But when you optimize, you essentially just need a method that's going to give you the next value of C.
Mm-hmm.
Right. And it turns out we can use sort of deep learning routines to give you the next value of C. And so that's why that can be done using Adam. And so once we get that value of C, just if we were to do a sort of a naive gradient update, there would be negative values. We can just threshold it, which effectively is like adding a ReLU at the end of that optimization.
Okay, got it. Got it. And thanks. And I have one question for the second project where you showed these propagation videos.
Okay.
And it showed that the model is able to correctly predict where the seizure starts spatially. Should we also be able to see this in the previous result where the model is highlighting in the different channels?
So yes, you can, but it's actually, so some of them, so this is a qualitative result in that we're able to extract a few of the examples that did this. In many cases, which is the case shown here, either it's very quick, so there might be 1 or 2 second wiggles that you're not really able to discern by eye, or it actually is flat. And so that was the motivation for the subsequent iteration where we decoupled that detection and localization.
I see. So how long are the snippets like each time point?
So every time step in the Markov process is effectively a 1 second EEG window.
I see. So this is like very small in this part here.
Yes, very small.
Okay. Cool. Thanks a lot.
Yeah.
Do you have time for another question?
Yes. Yes.
And maybe one follow-up to the first project. I mean, all three are very nice projects. Thanks, by the way. So the question is, how do you get from the DTI images exactly to this connectivity matrix? Or what is? So you said this is the tractography algorithm.
Yes. So let me just go back to the. You can.
And then
okay. Sure.
The size of this matrix, you mentioned you do it like per region. So the size of this matrix would be determined by the number of the regions squared, I guess.
So the model itself is agnostic. So you can substitute your favorite way of computing structural connectivity matrices. I believe what we do in this work is we run whole brain probabilistic fiber tracking and then do fiber counts between regions. And then we threshold it at something like 5 just to get some sort of sparsity. And then that is turned into a graph Laplacian.
I see.
And then the size, in this particular work, we use AAL, so 116 by 116. In other iterations, we've looked at smaller and larger parcellations. It does vary some of the parameters in that if you have a larger parcellation, you tend to need like a larger number of bases for these subnetworks. But overall, in terms of the prediction of the clinical measures, it does not improve it that much.
Thanks.
Are there more questions? If not, I would like to thank you once again, Archana, for the really nice talk and for accepting the invitation, first of all, and then for explaining a number of these works. Thanks a lot.
Thank you for the invitation.
Bye-bye.
Bye.